Okay, hello. This is the lesson about the sun. It's our nearest star. It's the source of uh, most of the energy on the surface of the Earth. And we're going to basically go through a general overview of the sun, talk about the sun's atmosphere. Yes, it does have an atmosphere. Go through its interior, focusing on the nuclear core. Then talk about solar magnetism. This is sort of something that we're getting a better understanding of recently. Now, first of all, we start with the sun itself. Again, the sun is a star. It is a star um, that is the closest to us because of its close proximity. It isn't oftentimes recognized as a star, but it's the same thing as all those bright points of light in the nighttime sky. It's just much closer than everything else. It's hundreds of thousands of times closer than the next nearest star, so it really dominates our sky. Now, comparing the sun, when we're looking at the sun, we're actually looking at, well, typically we're looking at the brightest part of the sun known as the photosphere. Now, if we were to place the Earth right next to the sun, it would be barely a speck on this diagram. The sun's more than 100 times the diameter of the Earth, and therefore, if we look at the total volume, it's more than 1,000,000 times the total volume. It contains 99.9% of all the mass of the solar system. It has so much inertia that it barely moves from its position while the planets go around it. Yes, Jupiter is over 300 times larger than our own planet in terms of mass. However, the sun is so much larger than Jupiter itself that even Jupiter isn't very much able to pull the sun from its position at the center. But Jupiter and the other planets do cause a little bit of a wobble in its position, but again, at 99.9, or more accurately, probably 99.89% of all the mass in the solar system, just about all the matter in the solar system is located in the sun. Now, its composition is that of the general, composition of the universe. The universe is dominated by hydrogen, so is the sun. The sun's 70% hydrogen. The next most common element in the universe is helium, and the sun has 28% helium. Of all the other elements that are present in the sun, about 2% are elements larger, I should say more massive than helium. So these are really trace gases. Later on, we are going to introduce this thing that you see right here. This is what's called an HR diagram. And it shows the position of different stars in terms of their brightness, what we call absolute magnitude. This is on a logarithmic scale, so it goes by powers, and temperature. On the scale, when you're looking at the scale, the cooler end of the scale is to the right, the hotter end of the scale is to the left, the dimmer part of the scale is to the bottom, and the hotter part is the upper part. So the horizontal axis is a little bit backwards, but hot is on the left, cold is on the right. In any case, when we're looking at the sun occupies a position nearly at the center of this diagram. What that means is that the sun is sort of middle in terms of properties of all the stars. It's what's called a G2 V. G2 represents the fact that it's sort of moderate in temperature. It's not very cool like the red stars. It's not very hot like the blue stars. It's right in the middle. The Roman numeral V means, or 5, means that it is actually what's called a main sequence star. And most stars spend their lifetime on the main sequence where they're converting hydrogen into helium. So let's go to the sun's atmosphere. The sun has 3 different parts to its atmosphere, 3 different regions that are really distinct. The lowest one is the most visible to us. It is called the photosphere, and photos, of course, means light. So sphere of light is very appropriate for this. And when we look at stars, in fact, any stars, because most of the light comes from the photosphere, that's what we're seeing. Now, there is an intermediate layer right above the photosphere called the chromosphere. Chromosphere is visible during a solar eclipse, And the chromosphere sort of has a pinkish color to it, and we'll explain why. The outermost layer is the most tenuous, but it's also the hottest, and that's the corona. So again, talking about the photosphere, that's what we see. The photosphere appears to be yellow in color due to its very high temperature. It has about the equivalent surface temperature of about 5,800 degrees Kelvin. It's the densest part of the atmosphere. It's the brightest part of the atmosphere, but it's the coolest part of the atmosphere. It is bright because of its high density. And again, when we're looking at the sun, almost all the light that we see is coming from this photosphere. Now, the photosphere is actually transparent. It's made out of hydrogen, helium, and some trace gases. But because of the sheer size of the sun, there's a limit to how far down we can see. We can only see down, well, roughly to about 1,000 kilometers. Now, on the very surface of this photosphere, the temperature actually drops down to about 4,400 degrees Kelvin. Down where we can not see anywhere below, the photosphere is about 6,600 degrees Kelvin. So when we're looking at the sun, we're sort of averaging those two temperatures. And again, we see an effective temperature of about 5,500 degrees Kelvin or about 5,600 degrees Kelvin. Now, the photosphere actually has some structure. If you really look at it carefully and you look at it close up, what you see in the photosphere are these granules. These are turbulent cells that last for about 5 to 10 minutes. And if you've ever watched the top of a boiling pot of water, this is exactly what the granules are like. It's like the boiling water coming up. But in this case, it's heat from the interior boiling to the surface. Nothing's really boiling here. There's no liquid in the sun. But like boiling, which creates convection, this interior convection, the hotter interior of the sun, trying to get heat outside to the cooler exterior, these convection cells, pop up and then disappear. And again, have a great deal of turbulence. At the center of these granules, they appear to be brighter and they appear to be higher in temperature because this is the hot rising gas on the upward phase of the convection. Around the granules where the gas is sinking back down after it's given off its heat, that material is darker, it's cooler. So again, each granule is an individual cell with hot rising gas in the center and cooler sinking gas toward the edges. Now, you can't really see this, but we've been able to image this on an even larger scale. The granules that you saw before are really very superficial. They're surface convection that doesn't penetrate very deep into the star itself. However, there are deeper convection cells which aren't visible to the eye, but are visible to special techniques that actually map the movement of the surface. Using Doppler measurements, where rising regions are blue, sinking regions are red, we can actually see the surface pushed up in certain parts and depressed in other parts. Now, these are called supergranules, and again, this pattern is not visible to the eye. It's only visible using very, very sensitive measurements of the surface. Of course, features that are visible on a much larger scale than the granules are sunspots, and this is something we're going to talk about in much greater detail later on. Sunspots are dark, cool regions on the sun's surface, and basically what happens is the sunspots are created when magnetic field lines break through the surface and block convection. The sun's extremely hot, and because of these high temperatures, many of the gases are actually ionized. Magnetic fields restrict the direction that gases can flow, or I should say ionized gas can flow, plasma can flow, and therefore it has a blocking effect where it comes through. So sunspots are a very good indication of where the sun's magnetic field is very intense and where the sun's magnetic field is breaking through the surface. Now, sunspots aren't actually black. They're very hot. They're about 37 degrees Kelvin. I should say 3,700 degrees Kelvin. And because the surrounding surface is 5,700 degrees Kelvin, they appear to give off much, much less light. If you could see the sunspots by themselves without the surrounding photosphere, you would see the sunspots to be actually red hot. Again, sunspots are magnetic in origin. Here's a close-up of some sunspots. And the interesting thing is you can actually see that the granules have been stretched out in the penumbra region around the sunspots. The black dark region is actually called the umbra. Other features on the surface are these things called faculae. Now, the sunspots are where the magnetic fields will block the heat from making to the surface. The facula are actually hotter regions on the sun's surface, where this blocked heat makes other avenues to the surface, and therefore they give off more light. So that's the lowest part of the atmosphere. High density, lower temperature, but definitely giving off most of the light from the sun, and therefore radiating the most energy away from the sun. The next layer is the chromosphere. And unlike the photosphere, the boundaries of the chromosphere are not really well defined. The chromosphere will go right from the top of the photosphere and sort of merge its way into the outermost layer of the corona. Now, the density of the chromosphere is much less than that of the photosphere, but it's significantly more dense than the corona. And as you can see in this eclipse picture, the chromosphere gets its name from its colorful hue. It's pink due to the hydrogen emission lines, where if we combine red and blue from these lines, in addition to some of the purple lines, it appears to have this sort of pink color. The proper name for this is actually magenta. Again, if we take a look at the spectrum of the corona, we can see, the chromosphere, we can see in this picture right here, where we only allow light from the hydrogen alpha line, that the sun appears to be sort of fuzzy. And that, again, is that chromosphere right above the photosphere. Here's looking at the chromosphere. Again, this is actually using blue light, not from the hydrogen beta lines, but actually filtering out the calcium atoms, which are ionized at the temperatures of the chromosphere. Again, if we were to create a spectrum of the chromosphere, we would see lines from both hydrogen and helium. Here we have the hydrogen alpha line right here, the hydrogen beta line, the gamma and the delta. Remember, the sun still has a large percentage of helium, so there is helium present there too, adding additional lines. A schematic of the cross-section right here, showing, first of all, the photosphere, the lowest part, then the chromosphere, shows that the chromosphere actually reaches up into the corona with these finger-like projections. They're called spicules, and they go up a very significant distance above the surface. Like the granules, they're actually temporary in terms of their structure. They last for only about 15 minutes. Now, the chromosphere is coldest where it meets the photosphere. It's only down to about 4,400 degrees Kelvin. And it's hottest where it merges with the corona, about 25,000 degrees Kelvin. We believe that the chromosphere actually receives its heat from the photosphere, the corona, and to some extent the sun's magnetic field. We now know that the sun's magnetic field does heat the corona, so there is a net flow of heat from the corona to the chromosphere. In the chromosphere, there is structure. There are filaments, which are basically gas that has been trapped by the sun's magnetic field. And in images of the chromosphere, these filaments appear to be black. There are also these other features called plages, which are basically light regions in the chromosphere, usually over sunspots where the magnetic field is intense, and the corona is being heated to very high temperatures. It's very strange. Where the sun's magnetic field makes it out of the photosphere, the photosphere gets cold because there's no convection to heat it up. But in fact, both the chromosphere and the corona get hotter near these magnetic field lines because magnetic field lines are able to heat them. And again, filaments, when the sun's disk is shown behind them, appear to be dark, but these same loops of gas and plasma actually appear to be light when they're seen on the limb of the sun. Now, prominences come in two different forms. Basically, are they active or are they not? Quiescent are not usually associated with massive X-ray explosions we call solar flares. Active prominences are typically associated with these types of actions. So basically, again, these structures are loops of hot gas trapped in the sun's magnetic field. Because the magnetic field loops from one sunspot to another, gas gets trapped between these two sunspots and just simply follows the magnetic field lines. Some of these prominences are exceptionally impressive just due to the sheer size. Here is what the sun would look like if we're next to the Earth were next to the sun. And for size comparisons, look at how big this prominence is compared to the Earth. Now, there is a transition region between the chromosphere and the corona. It's not really a significant area, but we have been able to see it using emissions from iron ions. So the outermost atmosphere is the corona. Again, we're going from coolest and densest to the hottest and thinnest, or least dense. The corona is the hottest and least dense. It'll extend several solar diameters above the sun's surface. And you can actually view the sun's corona during a total solar eclipse. The reason for this is the corona is very, very hot. It's so hot, in fact, it's over 1 million degrees Celsius, that almost all the electrons have been freed from their atoms. These electrons will take light from the photosphere and scatter them, much like our own sky scatters sunlight, and it produces sort of this ghostly white region around the sun, which is the corona. Now, the ions themselves don't radiate very strongly in the visible, so we don't actually see the gas molecules of the corona, or should say the plasma ions of the corona, in the visible light. We just see light scattered by the electrons. However, in the ultraviolet, you would actually be able to see the direct glow of the corona. Here's an ultraviolet image of the sun, and you can see that the corona actually has quite a bit of structure. You can actually see where the magnetic field will go from one sunspot and loop to another sunspot. Now again, the corona extends far into space. In fact, it sort of merges with the solar wind. So, you can't really say where the corona starts and where the corona, well, you can say where the corona starts, but you can't really say where it stops. Now, coronagraphs are basically made by blocking the light from the photosphere and allowing us just to see the light from the sun. In this coronagraph, it was taken from SOHO, the Solar Observation Heliospheric Observatory. And this shows the corona to be not all that even. It's very inhomogeneous. And it's actually composed of these long streamers of plasma that simply reach out into space. The streamers themselves are directed by the sun's magnetic field. And again, they represent places where the solar wind perhaps is leaving the sun. Now here's an image of the sun in the X-ray part of the spectrum. In the visible part of the spectrum, we generally see objects that are approximately the temperature of our sun's surface. When you go to the chromosphere and the corona, you have to look in the ultraviolet part of the spectrum just to see them. If we go one further out to the X-rays, X-ray light basically is given off by objects that have to be about 1,000,000 degrees or hotter. And of course, the corona is quite hot. But what we see in this X-ray picture is these bright regions are all above different sunspots. It clearly demonstrates that the sunspots where the magnetic field heats the solar corona, that is where the most energy is being deposited into the solar corona. Okay, talking about the sun's interior. The sun's interior can be broken into 3 basic zones. There's a core where nuclear fusion takes place. There's the radiation zone where energy is basically transported via X-rays. And then finally, there is the convection zone where energy is going to be transported basically due to the buoyancy of the hot gas. Now, again, when we're looking at the sun, all the energy is going to be essentially generated at the core. Here is where hydrogen is fused into helium. Okay? So essentially, this is where the energy is being generated. As hydrogen is converted into helium, some of the mass from the hydrogen is actually converted into pure energy. It's actually converted into gamma rays. These gamma rays can't go very far. They're basically deposited into the surrounding material. The core of the sun is very, very dense. The gamma rays give up their energy. That energy is then turned into X-rays. Well, the core is the only part of the sun which is hot enough and dense enough for this fusion to take place. So these gamma rays are basically going to heat the surrounding material, and then the surrounding material gets so hot, gets into the millions of degrees, that it's going to re-radiate it into the form of X-rays. Okay? So looking at this, I have to get to the sorry, skipped over there. Looking at this, once again, energy is created here. It's going to pass through this radiation zone in the form of X-rays, and then it's going to pass through the convection zone, basically where hotter gas is going to rise through convection and sink as it cools off after giving up its energy. Now, when we're looking at the sun, how do we know what's inside it? Remember, we can only see about 1,000 kilometers into the sun. Well, the reason we can see deeper into the sun is similar to the way we can see into the Earth's own interior. Every time there's an earthquake, seismic waves will go through the Earth and bend and travel at different speeds based on the Earth's interior properties. So this geoseismology has really allowed us to see what's inside the Earth. It allows us to see that we have a solid inner core, a liquid outer core, a somewhat solid mantle, and a solid crust. We know their density. We know their basic composition from density and the speed of the waves through here. We know just about everything we need to know about the interior of the Earth because of these seismic waves. We could do the same thing with the sun. However, placing a seismometer on the surface of the sun would be really, really difficult. Instead, because the sun is basically one big ball of gas, we can watch the surface and see as the surface moves using Doppler shifts to tell exactly how the waves are traveling through the interior. Now, the spacecraft that has been really involved in studying this helioseismometry or helioseismology is the SOHO spacecraft. It's a small satellite that sits right in front of the Earth as the Earth orbits the Sun. It sits in actually the L1 Lagrangian point. It's able to watch the Sun uninterrupted for 24 hours a day. And it watches the waves as they're generated basically by interior turbulency. I mean, we don't have earthquakes or sunquakes on the Sun. Instead, the turbulence inside the Sun creates these sound-like waves that bounce all over the interior and almost cause the Sun to act like a huge musical instrument. If you know what these waves should look like as you go through the interior, you can tell exactly what is going on inside. Now, the smallest waves, those with the highest frequency, as shown in red here, these waves don't travel very far into the interior. Okay? The small wavelength keeps them very close to the surface. So if you want to find out what's going on, just below the surface, you look at the higher frequencies of the different oscillations, by making these Doppler measurements. The deeper you want to look into the Sun, as shown in yellow and green here, the lower the frequency you have to look at. Finally, the very center of the Sun can be studied by looking at the lowest of the low frequencies. Now, initially, when helioseismology started, we were just looking at the very high frequency waves. And the reason for this was we could only watch the Sun so long as it crossed the sky before it set, and we had to start all over again. To get these really long wavelength waves, we had to watch the Sun for an extremely long time, maybe days, maybe weeks. And SOHO was one of the few instruments that is able to do this. The Sun never sets for it. It's always staring at the Sun. And by analyzing this helioseismic data, we can tell exactly what's inside. Okay, let's go through the different layers again. First of all, the outermost layer of the Sun, the convection zone. Basically, if you go from the very center of the Sun 2/3 of the way toward the center, that's the bottom of the convection zone. The convection zone goes from 2/3 out all the way to the total diameter to the surface. The temperature of this region is less than 2 million degrees Kelvin. Okay? At 2 million degrees, the gas is cooled off enough where the X-rays can't travel through it anymore. When it reaches the surface, the convection zone basically merges with the photosphere. So the top of the convection zone is simply the top of the photosphere. Now, we can imagine the heat from the interior reaching the bottom of the convection zone. That generates big convection currents in this deep convection layer, producing convection cells. There's another intermediate convection cell layer. This is what's probably responsible for the supergranules. And then on the very surface, we have the granules themselves, which are turbulent surface convection cells. Now, the other diagram that I showed you was sort of a schematic diagram, basically showing you a highly idealized, structure of the convection cells. This is an actual compilation of data taken from SOHO, and it clearly shows the rising and falling convection, the rising gases and the falling gases. Now, below the convection layer and right above the radiation layer is something called the interface layer. It's also known as the tachocline. The reason for this is the sun actually rotates slightly different in the convection layer than it does in the radiation layer. See, basically, because convection is taking place right here, all the gas pretty much has to move together. So everything's rotating at the same rate, more or less. Below that, however, there are different layers where you have faster rotating gas and slower rotating gas. Okay? This place where the gas suddenly changes rotational speed is known as a tachocline, and this is most likely responsible for the magnetic field that we see in the sun. The sudden change in these speeds causes the eddy currents to occur, and the eddy currents generate the magnetic field. Now, most of the time, the magnetic field has a very difficult time penetrating through the convection cells. Because convection cells have this circular motion and magnetic field lines don't like to move against this, we don't normally get strong magnetic field lines going through that. But every once in a while, you get one of these magnetic filaments, which breaks free of the tachocline and penetrates through the surface. And that's where we see the sunspots. Now again, the radiation zone, much hotter. As soon as you go above 2 million degrees Kelvin, right below the convection zone, the gas becomes transparent enough to X-rays, and therefore instead of being transported by convection, they can be transported by radiation. Now the bottom of the radiation zone is right where the core ends. At that temperature, it's about 10 million degrees Kelvin. Again, at the top, it's about 2 million degrees Kelvin. So the radiation zone is really from about 20% of the radius out to about 70% of the radius out. The interesting thing is, even though it's transparent to X-rays, the radiation zone does really impede the progress of photons. If you produced a photon of light at the core, it would take about 1 million years for that photon, if it just scattered off of everything, it wasn't absorbed, to actually make it to the surface. So again, X-rays are transparent to this, but there still is a lot of scattering that does take place, making it a very slow and arduous journey for the radiation. Now, the nuclear core of the sun is really the star's source of energy. Here, the density is high enough and the temperatures are high enough that hydrogen can overcome its electrostatic repulsion and it can be fused into helium. Now, the core makes up only about 20% of the radius of the sun. However, being at the center of the sun, it has a very high density and a very high temperature. Being that it's only 20% of the total radius of the sun, we have to raise this to the third power to find out its total volume. 0.20 raised to the third power actually places it at less than 1% of the total volume. However, it's so dense at the core that even though it's less than 1% of the total volume of the sun, it actually makes up 10% of the total mass. Now, the temperature of the core goes from 14 million degrees Kelvin at the center, where the reactions are most intense, to about 10 million degrees in the outer radius. The core has basically a mean density of 150 grams per cubic centimeter, or about 150 times the density of water. Again, the concentration of helium is greatest at the center, where the reactions go faster. There, the material might be as high as 65% helium and 35% hydrogen, whereas the very surface of the core, where very little fusion takes place, is 70% hydrogen, about 30% helium. Now, hydrogen fusion is an exothermic reaction. Two hydrogen fuse together to create a heavier isotope of hydrogen known as deuterium. In the process, they produce a positron. The positron annihilates with an electron, producing the gamma rays. The deuterium then fuses with another hydrogen. This produces a new element, helium-3. Helium-3 combines with another helium-3 to make helium-4. That's 2 protons, 2 neutrons, and 2 protons are liberated during the reaction. These protons are basically just 2 new hydrogen atoms. So 4 hydrogen produce 2 hydrogen plus, 6 hydrogen together produce 2 extra hydrogen plus 1 helium. Now again, heat is released from these reactions because they're exothermic. Gamma rays are generated, and the gamma rays are converted into X-rays. Now eventually, the sun's core is going to run out of hydrogen. When that happens, a strange thing will take place. Instead of the sun simply going dark and shrinking as it cools, the sun's core will actually shrink and get hotter, causing the outer layers of the sun to actually expand. Now, the subgiant phase of the sun is going to mean doom for the Earth. Even before the sun becomes a subgiant, life on Earth will basically have ended. The oceans will have boiled away because the sun is always getting brighter. At this point, when the sun reaches a subgiant phase, the Earth is going to be so heated that its atmosphere will simply boil away into space. Eventually, the shell around the core will continue to dump helium onto the innermost core. The shell around the core will cause the outer layers to expand even more. The sun becomes a red giant. And eventually, the core will become so dense that helium will fuse into carbon and oxygen and some other heavy materials. This will cause the sun to initially shrink back down, and then it'll begin to grow again. And basically, after growing and shrinking and then growing, the sun will become so large that it will almost definitely consume both Mercury and Venus. However, the Earth might just barely escape. There's some debate about our ultimate fate here on Earth. But one thing is certain. No matter what happens, life on Earth would become impossible. Even if the Earth were not consumed by a red giant sun, the sun's increased amount of energy generation would have long ago destroyed the atmosphere and really created a molten surface. So even if Earth survives, it'll probably be a molten ball due to the intense heat from the sun. Even the sun can't last forever. The red giant phase is really a last dying phase of the sun. The outer layers of the sun will simply blow away into space. The sun will become a planetary nebula. And eventually, what is left behind is only the core of the sun. It'll shrink to become what is called a white dwarf, which is basically just a dead ember of a star. It'll have about the same size of the Earth, but still be pretty close to the mass of the sun. Okay, let's talk about the sun's magnetic activity. We know where the energy is coming from. The energy is generated in the core, it makes its way to the surface through the radiation zone, And then after the radiation zone, it travels through the convection zone where it's radiated into space by the photosphere. Now, the magnetic activity of the sun, however, slightly alters the sun's appearance. As we said before, the magnetic field, as it breaks through the surface, actually generates these sunspots. We have observed, however, that the magnetic field and the sunspots seem to come in cycles. We call this a solar cycle. Every 11 years, the sun waxes and wanes through these cycles of increasing and decreasing sunspot numbers. Sometimes there are a lot of sunspots. Sometimes there are very few. We call the peak of sunspot and magnetic activity solar maximum. In this graph, we see the number of sunspots per given time and the year that they were observed. In the last solar cycle, it seemed to peak around 2001. Currently, we're going through another solar cycle. The peak seems somewhat around 2013. However, because it really hasn't peaked yet, we don't know where that peak is going to lie. So during solar maximum, the magnetic field produces a lot of sunspots on the surface. During solar minimum, there are very few sunspots, and the magnetic field is very orderly. In fact, the sun's magnetic field during solar minimum almost looks like a bar magnet. Sort of resembles our own Earth's magnetic field, where it has a very well-defined north field and a well-defined south field. Just the opposite happens during solar maximum. The field becomes very chaotic. There are many sunspots which have local north and south polarity. In addition to that, there's a tremendous number of storms, solar storms, all due to this magnetic field. Now, why solar minimum and solar maximum happen seems to be related with how the magnetic field of the sun constantly resets itself. During solar minimum, all the magnetic field lines are basically very orderly. They point from south to north. But the sun doesn't rotate at a constant rate. The equator actually rotates faster. And because the sun is very hot, the ionized gas within the sun actually drags these magnetic field lines with it, causing magnetic field lines to wrap around and wind much like a rubber band. Eventually, these magnetic fields begin to break through the surface, producing the sunspots. When the magnetic field lines snap, they can create a very intense burst of energy. And again, the magnetic field lines breaking through the surface produce a pair of sunspots. Typically, one has a polarity of north, the other one has a polarity of south. In very complex sunspots, you can have multiple north and south poles. Now compare the two images that you see here. Both were taken in the ultraviolet part of the spectrum. Therefore, they look at the chromosphere and the corona, which are most affected by the magnetic field. The image on the left barely has any structure to it. You might be able to see some magnetic field lines at the North Pole and South Pole, but for the most part, it's very orderly. In the other diagram, we see multiple bright spots, each of which is above a sunspot. Okay? Again, left is solar minimum, right is solar maximum. And you can clearly see the difference in the magnetic field during the two states. So again, the sunspot's a region where the magnetic field line breaks through. Typically, a loop across the surface and reconnect at another sunspot on the photosphere. And it's these magnetic field lines which are responsible for a number of different phenomena. Now again, although the surface of the sun is too cool for hydrogen and helium to ionize, heavier elements such as some of the metals, calcium, iron, are ionized, and they must move along the magnetic field lines due to the fact that they have charge. The problem is the magnetic field lines are pointing out of the sun. Convection is a circular current, so there has to be horizontal motion to complete the cell.
The circular convection cells therefore cannot develop in these magnetic regions, and it basically traps the gas and prevents the gas from getting more energy from beneath the sunspot. Therefore, it tends to cool off more. If we look inside the sunspot, we see that they actually have quite a complex structure where the magnetic field lines basically radiate from the interior. And here's a real close-up of the sunspot. You can see the normal granules up here, and these granules are being stretched in the penumbra of the sunspot due to the magnetic field. SOHO has been able to actually look deep into the sunspots, and we see that they're not just on the surface. They do go quite deep because the magnetic field lines penetrate all the way to the tachocline. Some models of these sunspots seem to indicate that although the sunspots shouldn't theoretically be stable, the sunspots actually create a similar structure to what we see in things like cyclones and other rotating storms. And this rotational motion actually stabilizes the sunspot, keeps them from flying apart. Now, one of the most violent events on the surface of the sun is a solar flare. A solar flare happens when the magnetic field lines suddenly break, and this change in magnetic field rapidly heats any gas trapped within these magnetic field loops. Here's an ultraviolet image of one of these solar flares. Now, the solar flares really cannot be seen in the visible part of the spectrum. If you're looking at the sun when the solar flare happens, you will not notice that it takes place. However, if we look in the ultraviolet part of the spectrum, solar flares are very obvious because the ultraviolet part of the spectrum, this hot plasma, which is being heated by the snapping magnetic field lines, glows very strongly. To understand how solar flares are created, we have to understand how the magnetic field lines can evolve. In this particular example that we see here, we see a big coronal mass ejection which followed a solar flare. Essentially, two sunspots were close to one another, and the magnetic field line looped from one to the other. This loop trapped gas, but when the magnetic field line started bending out towards space, the field lines would snap, and this would induce a huge current and rapidly heat this gas, which would explode, producing a flash of X-rays and a flash of ultraviolet light, and then this gas would just blow into space. Now, we ranked solar flares on a logarithmic intensity scale. Basically, the weakest flares are called A flares, but they're always present. They're not really even worth considering to be flares. They're, so low power, essentially, that, small granules can generate them. B-class flares are about an order of magnitude greater. They're very frequent. Their X-ray intensities are difficult to detect against the general X-ray background because, again, the sun is constantly generating X-ray noise due to the movement of these different granules or due to very minor activity in solar flares. C's are common in terms of during solar maximum, maybe less common during solar minimum, but again, not all that rare. M classes are extremely strong flares, and X class flares are the most extreme flares. It's very unusual to have the intensity into the X class, but during the last solar maximum, there's actually quite a few examples of X class flares, in some cases occurring in the same week. One of the most intense X-rays ever recorded was recorded at an X28 level. Basically, an X1 flare is 1/10 the intensity of an X10 flare. It's a logarithmic scale, basically, the way that works. An X20 flare is 100 times the intensity of an X1 flare. So this X28 flare was almost 1,000 times the most intense flare, the minimum flare to be considered X. Now, this largest flare was recorded on November 4th, 2003. In fact, it was so intense that we had to estimate its magnitude. We couldn't directly measure it because the satellites that typically measure it were actually put in safe mode. They actually had to shut down due to the intense radiation from this event. Again, how do we produce one of these flares? Well, we have a sunspot here and a sunspot here, and a magnetic field in between. Gas and plasma are trapped between the magnetic field lines, but as the magnetic field lines bend upward into space, they begin to break and then reconnect. As they do so, any changing magnetic field can induce a current. In fact, that's how a generator works, right? You rotate the generator, which rotates the magnetic field within the coils of wire, and these conductive coils of wire generate a voltage from that. Well, the solar flare is pretty much the same thing. You're producing this changing magnetic field, but instead of a rotating magnetic field, the magnetic field lines are changing because they're breaking. And as they rapidly break, they take the hot conductive plasma and they basically produce a very large current, like an arc welder. The plasma gets so hot that it almost explodes, releasing, again, these coronal mass ejections. And, as the gas gets hotter and hotter, as the plasma gets hotter and hotter, it glows stronger and stronger in the X-ray and the ultraviolet part of the spectrum. These flares also accelerate electrons. The electrons accelerate near the speed of light near the sun, causing a huge release of radiation. It's hard to get a good picture of an actual solar flare. Typically, the pictures that we get that show any detail whatsoever, because the flares are just so bright, are these post-flare loops. You can clearly see that there's still loops going from one sunspot to another. And these post-flare loops were actually recorded following the X28 solar flare. And you can still see that the gas is very hot. It's still giving off very intense ultraviolet light due to the original explosion. As the magnetic field lines break during the solar flare, oftentimes the trapped plasma, at least some of it, ends up escaping to space. This coronal mass ejection was captured using a hydrogen alpha filter, and you can see what it looks like in terms of the size of these big magnetic clouds compared to the sun. They're massive. But the coronal mass ejection is basically just a big blob of very hot plasma. It has a magnetic field of its own, and when it hits the Earth, it's going to affect the Earth's magnetic field. Here's a nice sequence of pictures showing the initial solar flare, then the gas leaving magnetic field lines. And then you see all these speckles all over the pictures. Basically, these speckles are radiation particles that are hitting the detector, causing this snow or interference. Here's another large coronal mass ejection. Here's the sun. You can see that this thing's bigger than the sun itself. So on Earth, we are affected by these solar storms because as these magnetic fields hit our own magnetosphere, it squeezes the magnetosphere and it causes these particles to actually fall out of the radiation belts. Now, when these magnetic storms arrive at Earth, they can generate very, very large currents. Remember, the solar flare was actually generated when the magnetic field lines broke and rapidly changed. When our own magnetic field rapidly changes, and when this big ball of magnetized plasma makes it to the Earth, okay, this rapidly changing magnetic field can induce huge currents in both satellites and in power grids. In fact, one of the biggest solar storms that we experienced in modern times in 1989 created a massive power outage, primarily in Canada, which is more susceptible to these magnetic field lines because it's closer to where the magnetic field line connects back to Earth. But the other interesting phenomenon that we see during these storms are these northern lights, or southern lights if you're in the southern hemisphere. And as the electrons and protons are squeezed out of the Earth's own radiation belts and magnetic field, they rain down typically in polar regions, and when they make collisions with the upper atmosphere, they ionize the air molecules, causing them to glow different colors. And again, you can produce very, very large induced currents through these solar storms. All you have to do is rapidly change the magnetic field, and the changing magnetic field will create a voltage induction, and these are known as Peterson currents. These can create large currents within our own atmosphere, but also large currents on the ground. Here's a view of the aurora from space in the top picture and from the surface of the Earth in the bottom of the picture. Again, as the electrons excite the oxygen and nitrogen molecules in the atmosphere, we get all different colors. We get reds, we get greens, we get blues, depending on what molecules are being excited. Look far up in space, the aurora appear to be an oval over the poles. These pictures are actually taken using ultraviolet light, where the ionized gas glows very strongly. You can clearly see that the aurora itself extends in sort of this oval structure. This one would have only been visible in Canada, not down in the United States. Now, back to the solar wind. When these coronal mass ejections happen, it's just a huge cloud of magnetized plasma that can interact in not such great ways with our Earth's own magnetic field. Fortunately, we are protected by a magnetic field, and it does shield us to some degree, but not completely. Even when the coronal mass ejections don't happen, it doesn't mean that the sun's not losing matter. The sun is always shedding matter in the form of solar wind. And this solar wind is composed of mostly simple protons and electrons, basically the building blocks of hydrogen, but there's also a less significant component of heavier elements: helium, lithium. What else do we see here? Iron, silicon, magnesium. The solar wind is not constant with time, but it's also not constant with direction. Along the equator of the sun, which our Earth actually sits in the plane of the sun's equator, the solar wind is actually much lower because that's where the magnetic field lines trap the solar wind. But at higher latitudes, away from our own position, the speed actually becomes greater, as does the density. Again, the solar wind is directed by the sun's magnetic field. The Earth's own magnetic field, the magnetosphere, does shield us from most of these particles which would be harmful. The pressure from our sun's solar wind extends far out into space, far beyond the planets. And this is called the heliosphere. It's sort of hyperbolically shaped because the sun is actually traveling through space, causing this magnetic field and solar wind to actually almost look more like a comet. The place where the pressure of the solar wind is equal to the pressure of other objects in our galaxy is called the heliopause. But that's really the furthest that our sun's influence stretches. Okay, well, that is our lesson about the sun. I will post that up on the archives and hopefully be able to schedule a session for us real soon.